Hi, and welcome to part 3 of this tutorial. My name is Yibo Yang, and let's take a look at lossy compression with machine learning. I'll start with some background on lossy compression under the usual rate-distortion criteria. Then I'll introduce nonlinear transform coding, which is currently the predominant paradigm for neural lossy compression. Then I'll consider some additional criteria for lossy compression, such as perceptual quality and performance on downstream tasks. Then I'll go beyond image compression and give you a flavor of video and point cloud compression. And finally, I'll hand over to Karen, who will talk about relative entropy coding, which in principle allows us to use any kind of latent variable model for compression. Let's begin by trying to characterize mathematically what's really going on in lossy compression. In general, lossy compression involves 3 random variables: the data random variable x, which follows some unknown distribution that we typically assume is ID, the linear representation z, and then a reconstruction x hat. These 3 random variables form a Markov chain in the sense that the reconstruction is conditionally independent of the original data given the representation. And the lossy compression procedure then consists of an encoder that maps the data to a representation and the decoder that maps the representation to a reconstruction. We're being fully general here and allow both maps to be either deterministic or stochastic. You may also notice that this Markov chain describes what happens in the training step of a VAE, where we will feed the data through an inference network and obtain a latent representation, and then run the representation down a sampling path to obtain a stochastic reconstruction. But note that there is one important distinction between latent variable modeling and compression. That is, in compression, the representation has to be communicated over a digital channel. And as we'll see, this has consequences for how we design and train these models. Here's a routine example of lossy compression, that is image compression, but it can also be more abstract. For example, we can think of the way that we humans communicate in words and symbols also as a form of lossy compression. In the introduction, we saw many good reasons for why we want to use lossy compression. So how should we go about being lossy? Well, we'll need to throw away a lot of irrelevant information, and also not so much information that the reconstruction contains no useful information of the original data. So a key question is this: what information is relevant versus irrelevant, and how do we know if our lossy compressor is doing a good job? We'll come back to this question many times later, but for now, we'll consider a basic and also very well-established approach, and also the one originally taken by Claude Shannon. The idea is this: we will quantify the relevance of our reconstruction by looking at how much distortion or deviation there is between the reconstruction and the original input data. And to do this, we assume that we're given some kind of distortion function rho, and most often this is a squared error or a mean squared error. We'll also revisit this choice later on. And next, we will transmit the representation losslessly. And for this to be possible, we require the representation to be discrete. That is, it can only take a countable or finite number of values. And I'm denoting it by z hat instead of z to emphasize this. And furthermore, we'll need a prefix code to convert z hat into bits. And as we learned from lossless compression, this is equivalent to choosing an entropy model over z hat, from which we can always derive a prefix code. So we'll just work with the entropy model from now on. Given the above, the goal of lossy compression then is to choose a lossy codec consisting of an encoder, decoder, and entropy model that simultaneously minimizes both the bit rate and the average distortion. We can plot these two quantities for any compression algorithm, and our goal is then to push the rate distortion performance of our algorithm towards the lower left corner of this plane. And unsurprisingly, there is a trade-off between rate and distortion, and there's a limit to how well we can do. And we'll look at this next. In lossless compression, we learned that the entropy is the fundamental performance limit. And in the lossy setting, an analogous quantity is the rate distortion function of the data, as originally defined by Shannon. And to define this object, here we'll abstract away the latent representation and consider our lossy codec to be any stochastic mapping from the input data to the reconstruction. And it turns out that the mutual information between the data and the reconstruction, as induced by this stochastic mapping, is a fundamental measure of bit rate. That is, the average number of bits per sample needed to transmit x hat given x. And for a given distortion threshold d, the rate-distortion function finds the minimum of this mutual information over all the stochastic maps that satisfy the distortion threshold. Borrowing this constraint optimization idea, we can define the operational rate-distortion performance of our codec in a similar way. But this time, we'll minimize the actual code length instead of the mutual information. And it turns out, as proven by Shannon, that the operational performance of our codec can never be better than the rate-distortion function. But on a more positive note, the rate-distortion function is also achievable by compressing multiple data samples together in increasingly long blocks using vector quantization. So combining the above, the rate-distortion function gives us the best achievable performance of lossy compression by any algorithm as measured in rate and distortion. And in picture, what this means is that the rate-distortion function of the data, as shown in this blue curve here, separates the kind of rate-distortion performance that is possible versus the impossible. Now let's look at some concrete implementations of a lossy codec. Vector quantization, or VQ, is perhaps the most basic and most generic form of lossy codec. The idea here is to encode a data vector by mapping it into an integer value representation. You can also think of this as an index. And then we decode by indexing into a codebook of reconstruction vectors. You're likely already familiar with this idea from k-means. And indeed, the k-means algorithm constructs a locally optimal vector quantizer, assuming a fixed length code. That is, it assumes an entropy model with equal probability for every index. Of course, we can do away with this restriction and estimate a flexible entropy model and augment the k-means objective to also penalize the expected code length under this entropy model. And this gives us better rate-distortion performance and is the idea behind a classic VQ algorithm known as entropy-constrained vector quantization, or ECVQ. There are also other types of vector quantizers, but a common issue with all of them is that they don't scale very well computationally. As we increase the number of data dimensionality, the number of codebook vectors needs to grow exponentially for VQ to perform well. As a result, VQ is most commonly used in low bitrate applications such as speech and audio. However, I do want to point out that the k-means style vector quantizer has been used successfully as an image tokenizer in popular deep generative models such as VQ-VAE, DALI, and VQ-GAN. Another classic codec goes under the name of transform coding and overcomes the computational issues of VQ. I already saw an example in JPEG earlier. The basic idea here is to do the quantization in a transform space, where a simple and cheap scalar quantizer can already give us good performance. The encoder now splits into an analysis transform followed by a scalar quantizer, and most of the time this is element-wise rounding to integers. And the decoder computes the inverse of the analysis transform, often known as the synthesis transform. And here's what it looks like when we run this algorithm on our toy example. The data gets mapped to transform coefficients, which are then rounded coordinate-wise into integers, and then entropy coded under some entropy model and given to the decoder, who then computes the reconstruction. Note that the reconstruction points here now form a lattice instead of being allowed to be arbitrary points as in VQ. In traditional transform coding, the transform is linear and often unitary. This allows us to do some theoretical performance analysis, and this choice can even be shown to be optimal when the data source is Gaussian. And transform coding is computationally much more scalable than vector quantization and is currently the most widely used form of lossy codec for digital media such as images, videos, and audio. Now let's talk about nonlinear transform coding, which is currently the predominant paradigm in neural lossy compression. Given what we've seen about transform coding, the idea behind nonlinear transform coding is actually quite straightforward. That is, we'll upgrade various components of transform coding with neural networks and train them into informed data. And this idea should be familiar to us by now, seeing how deep learning has been applied to revolutionize speech and NLP and many other fields. So we'll no longer restrict ourselves to linear and often data-independent transforms as in traditional transform coding, and instead we'll use a pair of encoder and decoder neural networks. We'll also learn an expressive entropy model, often borrowing ideas from neural lossless compression. Our goal, as before, is to optimize the rate-distortion performance, and a common objective function is a linear combination of the two losses, weighed by some hyperparameter, determining the trade-off between the two. And to give you a concrete example of what this looks like, here's a basic architecture from image compression, known as compressive autoencoder. So here the encoder network consists of a few layers of convolution with downsampling, and the decoder is another convnet with transpose convolutions and upsampling. And the entropy model here is fully factorized and uses one independent density estimator per latent dimension, or rather per latent channel. And here's what it looks like when we apply a basic nonlinear transform coding algorithm to our toy example. It's pretty much the same picture as before in transform coding, but note that the reconstruction points now better adapt to the shape of the data, which has a banana shape. Now let's turn to the important question of end-to-end training. Ideally, we would like to optimize the operational rate distortion performance. However, the quantization operation is not differentiable. It kills off any gradient signal going to the encoder. And moreover, the entropy model is technically a probability mass function and does not have a gradient defined with respect to its discrete input. And one solution to this problem, which has worked pretty well and become really popular, is to replace rounding with adding uniform noise. Specifically, the noise comes from a uniform distribution between negative 0.5 and positive 0.5. And the intuition here is that in many settings, the residual error from rounding often follows a distribution like this, at least approximately. And instead of working with a probability mass function for the entropy model that we denoted by P, we'll instead use a continuous density model, P tilde, that extends P from integers to real values. And this results in a good approximation to the discrete rate loss, which is the first term in the RD loss. We've actually seen an example of this idea, this discretized density model, in Pixel CNN++ from lossless compression earlier. Now we'll take expectation with respect to the noise, and we end up with an objective that is fully differentiable and can be used with SGD for end-to-end training. Over the years, many other solutions have been proposed to deal with quantization and to enable end-to-end training. And here are references to some of the notable ones. For example, the ones based on straight-through estimator, which has also been used to train discrete normalizing flows. Not all of these methods quantize to integers, and different methods can be useful in different problem settings. Now let's take a closer look at the uniform noise approximation for end-to-end training. It turns out that we are equivalently also learning a variational autoencoder of the data. To see this, consider a VAE whose inference path is given by adding uniform noise to the output of an encoder. And let's call the resulting random variable z tilde. And this corresponds to an approximate posterior distribution with a uniform density centered around the encoder prediction f of x with width 1. And to generate a data point, we'll first draw a sample of z tilde from our prior, which is this density model p tilde defined earlier. Then I'll run it through an encoder network, and finally add some white Gaussian noise. And specifically, the variance of the noise will be inversely proportional to lambda, which is the trade-off hyperparameter in our RD loss. And together, this defines a Gaussian likelihood model centered with mean equal to the reconstruction x hat and variance proportional to 1 over lambda. And finally, let's write down the negative elbow objective that we minimized for training this VAE. We see that the log posterior density term evaluates to 0. And then we apply the reparameterization trick, and this gives us the same rate distortion objective for end-to-end training as before, under a squared error distortion function. And this connection between lossy compression and latent variable modeling allows us to apply ideas from generative modeling to lossy compression. Neural lossy compression based on nonlinear transform coding is now an active area of research, and here I'll take a look at a few main directions. One is improving the entropy model, and we'll see many ideas from neural lossless compression here again. To make the factorized entropy model more expressive, a common approach is to use another latent variable to model the latents themselves. And we do this by augmenting the existing generative hierarchy with another hierarchy of latents called hyperlatents. And hyperlatents can be quantized to integers and learned with the same uniform noise approximation as before, but we can also get bits back from them. We can also use an even deeper hierarchical VAE, such as a ResNet VAE with bidirectional inference. Another idea is to use an autoaggressive entropy model, and this can be defined along a spatial ordering, like in pixel CNN, and it can be used in conjunction with hyperprior. But a common issue with this type of approach is that the autoaggressive model defined along spatial ordering can be slow to draw samples from, and in our case, can be slow to decode. So there are many other ideas, all with the goal of giving us an expressive autoaggressive model without being super slow to decode. For example, we can define the autoaggressive ordering along the channel dimension, or spatially via checkerboard patterns, or introduce attention mechanisms, or even use a vision transformer. Another line of research aims to improve the encoding procedure of neural lossy compression, and this has connections to variational inference. To encode a data point, instead of quantizing the representation computed by our encoder network, we can instead iteratively optimize the representation as shown by this trajectory in this picture. And we found that the resulting representation gives us significantly improved rate distortion performance. Related to this, there have also been several methods aimed at closing the discretization gap between self-quantization used during training and hard quantization at test time. These methods often are based on annealing. Yet another idea for inference optimization is to adapt or overfit the parameters of the whole model on the data instance being compressed. And finally, there's also work on improving the transforms in nonlinear transform coding. And the overall idea here is to make the transforms more efficient and more effective at decorrelating the data input. For example, people have used residual connections, attention mechanisms, and even vision transformers. Invertible neural networks have also been proposed for improving compression performance in the high bitrate regime or for near lossless compression. Let's take a step back from all this research and ask ourselves where the field is now in 2022. And I'll focus on neural image compression, which has been studied extensively since 2016. And these neural image compression methods have made steady gains since then and have now exceeded the traditional ones in rate distortion performance. Here are some example rate distortion curves on a common benchmark. And technically, these should be called quality rate curves. On the x-axis, we have the bit rate measured in bits per pixel, and on the y-axis is the quality of the reconstruction as measured in PSNR. And this is really just the inverse of the mean squared error on a log scale. So the higher the better, and this is the opposite from the rate distortion pictures we've seen earlier. So you just have to mentally flip everything upside down. Now, this plot is by no means exhaustive. I included two of the most recent state-of-the-art methods that I could find, as well as a few earlier methods that are now considered landmarks in this field. And as you might notice from these curves, over the years, it's becoming increasingly competitive to try and beat the state of the art. So you might wonder, is there a limit to how much further we can go? And unfortunately, the answer is yes. And as we learned earlier, one such fundamental limit is given by the rate-distortion function of natural images. And outside of a few toy cases, the rate-distortion function is unknown analytically for most of the real-world data of interest to us. But it's possible to estimate it numerically using data samples. So in my work, I've shown that it's conceptually straightforward to approach the rate-distortion function from the above using a VAE, and I estimated an upper bound on the rate-distortion function of natural images, plotted here in blue. Note that an upper bound on the rate-distortion function represents theoretically achievable rate-distortion performance. And here there is still a comparable gap between this blue upper bound that I estimated a year ago and the state-of-the-art methods, with the gap here highlighted in cyan. So it seems like there's still quite some ways to go before we hit the information theoretic limit. It'd also be nice to bound the rate-distortion function from the other direction, which would really tell us when we've hit a performance ceiling. I've made some progress on this problem in the setting where the data has low intrinsic dimension, but the problem in general remains quite challenging. To recap, our criteria for lossy compression so far have been rate and distortion. And now let's add perceptual quality to the list. And this is a relatively new frontier, and where neurocodecs can be expected to really have an advantage over the traditional ones. For compressing digital media, such as images, low distortion is ultimately just a surrogate for good reconstruction quality as perceived by human users. However, it turns out that these two criteria are not necessarily well aligned. It's been observed many times that the mean squared error does not predict perceptual quality very well. And here's a classic example. The image on the top left corner is the original one, whereas the 5 other ones are all corrupted versions obtained by, for example, shifting the original one by a few pixels or compressing it with JPEG. Now, all these 5 images have the same mean squared error relative to the original, yet we perceive them to have very different perceptual quality. One potential solution to this problem is to use a distortion function that is more in line with our human perception. And a classic example of a perceptual distortion, or a quality metric, is the structural similarity index measure. It's computed by breaking the 2 given images into little patches and comparing the statistics of pixel values between corresponding patches. And it's been shown to work much better than the mean squared error at predicting common distortion artifacts, such as blurring or blocking. Another class of perceptual distortion is derived by comparing the distances between features extracted from deep neural networks. And these are often pre-trained vision classifiers, such as VGG or AlexNet. And a common example of this is known as LPIPs. Now, many such distortions are differentiable, but using them for end-to-end training can give us mixed results. Basically, the compression model can learn to exploit whatever blind spots there is in this distortion function, so we can still end up with artifacts that are specific to the kind of distortion function used for training. To show you an example of this, here is on the left a reconstruction from a model optimized for the SSIM, whereas the reconstruction on the right is from a model optimized for mean squared error distortion. And you can see that the reconstruction optimized for SSIM gives us sharper and crisper reconstruction in this grassy region. However, it also gives us worse and blurrier reconstruction in this text region on the airplane. So how can we get artifact-free reconstructions? Or is it even possible? Well, for this, we can consider a different notion of perceptual quality, one that is independent from looking at the input or the reference data. The basic idea is that we will consider a lossy compressor to have good perceptual quality if it's hard to distinguish its output reconstructions from real data. And one way to mathematically quantify this distinguishability is with a binary hypothesis test. So here we'll draw a sample each from the data distribution and from the reconstruction distribution. Then we'll flip a coin and present one of them randomly to a discriminator and let them guess which distribution the sample came from. And it turns out that the highest probability of success by any discriminator on this test is proportional to the total variation distance between the data distribution and the reconstruction distribution, plus 0.5. So this suggests that we can use this divergence between these two distributions as a way to quantify perceptual quality or realism. And again, the intuition here is that compression artifacts are what give away the fact that we're looking at reconstructions instead of real images. And if the reconstructions are indistinguishable from real images by any discriminator, then we've achieved perfect perceptual quality or realism. And in this case, the divergence will be 0. Here are some examples of non-reference perceptual quality metrics. You've likely seen them, such as the FID in the context of evaluating samples from GANs and other deep generative models. And all of these metrics are based on a similar idea, which is to compare the distributions, often in Wasserstein distance, of the features between natural images and the fake images. And again, the features are extracted from a pre-trained vision classifier, such as Inception v3. And the fake images here are computed as reconstructions and to follow the marginal distribution of reconstructions from our compression algorithm. So we looked at how to evaluate realism, namely with a divergence. Now let's talk about end-to-end training. And the general idea here is to minimize a combination of rate and distortion and divergence. And a basic thing we can do is to reuse the compressive autoencoder architecture from before, but add a discriminator. So in practice, people often replace the divergence term with the GAN loss during training. And this is the standard GAN loss, but with the decoder serving as the generator of the GAN. And often the discriminator is also conditioned on the latents, and this has been found to give sharper reconstructions. It's also possible to use semantic labels, such as object bounding boxes, to guide the generator to selectively hallucinate certain parts of the image, while preserving the more relevant parts to have low distortion. And this can give us further bitrate savings. Of course, other divergences are also possible. People have investigated Wasserstein distance and KL divergence in the case that a diffusion probabilistic model is used as the decoder. And here's an example from a state-of-the-art generative image compression model targeting realism. And you can see that the model's reconstruction on the left looks much better than JPEG, despite using half the file size. But if you look really closely and you really zoom in on the images, you'll see that the model's reconstruction actually differs very slightly from the original in the texture details. So GAN-based models, like the example we saw earlier, have become quite good at producing realistic reconstructions. And you may ask if it's necessary to train on both a distortion and a divergence. And can we achieve the same effect with just a well-designed distortion alone? And it turns out the answer is no, in the sense that there exists a fundamental trade-off between distortion and perceptual quality as measured by a divergence. At a high level, this means that the best achievable divergence can only become worse as we demand lower distortion. This result has also been extended to the lossy compression setting. It's been shown that there exists a three-way trade-off between rate and distortion and perception. The result has a similar flavor, that is, optimizing for perception or realism comes at the cost of worse redistortion performance. And a few recent studies have studied the amount of redistortion performance that we have to sacrifice in order to achieve perfect realism or artifact-free reconstructions. Now let's switch gears and consider a setting where we don't really care about perceptual quality. Here's a motivation. A huge amount of data, such as climate data, satellite images, or data captured by autonomous vehicles, will only be seen by algorithms and machines that process them, and will never be seen by humans. And for storing these kinds of data, the perceptual quality is irrelevant, and we only care about preserving the downstream task performance when using the compressed representation. Let's formalize this problem mathematically. We're given pairs of x and y from some joint distribution. Here x is the same data random variable as before, and y has the interpretation of a target or a label that contains the supervision signal for the task. And the y is available to both the encoder and the decoder. As an example, the task could be semantic segmentation, where x is an image and y contains the ground truth semantic labels for every pixel in the image. Our compression algorithm takes in data sample x and returns a compressed output that I denote by z. This z is what's used for the downstream task instead of the original data x. The bit rate of our compressor can be measured by the mutual information between x and z. This is what we did in rate-distortion theory. Or in practice, this is often just measured by the Shannon entropy of the variable z when we use a discrete representation for entropy coding. Given this setup, task-oriented compression can be understood as optimizing a rate and distortion trade-off, but with a distortion defined by some performance metric on a downstream task. And different methods make different choices of this distortion. One known example of this is the information bottleneck principle. And the information bottleneck principle optimizes an abstract task loss as measured by the negative mutual information between y and z. It essentially captures the predictability of y given z. As a more concrete version of this approach, in feature compression, we'll typically use a concrete task loss from some prediction. For example, the cross entropy between our prediction and the ground truth label, or a squared error loss in the case of regression. We can train end-to-end neural compression codecs on these losses using the same techniques that we discussed before in nonlinear transform encoding. There's also research that studies the multitask setting, where the goal is to learn a representation that preserves downstream task performance on a variety of different tasks. The neural compression methods we've looked at so far were mainly developed for image compression, where we have a good set of tools for handling images, such as convolutional neural networks. Now we'll take a high-level look at two other data modalities, videos and point clouds. And due to the high volume and dimensionality of such data, we often need to be more careful about how we feed them into our neural networks. And the research so far has mostly focused on lossy compression with rate and distortion being the criteria. Let's take a look at video compression. A video is just a sequence of images or frames, and besides spatial redundancy among the pixels within each frame, there's also strong temporal correlation across the different frames, which we'd like to exploit to reduce the bit rates. Let's take a look at one popular approach known as predictive coding. Here we'll compress the frames sequentially, and we want to compress a ground truth frame at a current time t. And the basic idea for predictive coding is to use the previously compressed frame to form a prediction of the current frame, and only compress the difference between the prediction and the current frame, known as the residual. And if we do this prediction step well, then the residual will mostly contain zeros and will be easy to compress. And this residual can be compressed with any image compression algorithm like the end-to-end method we've discussed so far. And the decoder will do three things. First, it receives the residual. And second, it forms its own identical copy of the prediction, possibly with the help from the encoder in the form of another bit stream containing instructions. And finally, it adds the residual to the prediction to form the reconstruction. And we repeat this process over time, and we will use the current reconstruction to form the prediction of the next frame. This predictive coding approach has been very popular and has worked very well in both the traditional codecs as well as neurocodecs. And these neurocodecs swap out the various components in this diagram with neural networks, and they are starting to outperform the traditional codecs in rate-distortion performance. There are many other possibilities for video compression, and some recent neural codecs do not use predictive coding at all and have still obtained good performance with a powerful autoregressive entropy model, taking inspirations from large-scale language modeling. Now let's take a look at point cloud compression. A point cloud is simply a collection of points in 3D space, often billions of them or even more in a 3D scene. And often each point has an attribute like a color or intensity associated with it. And for simplicity, we'll not deal with the attributes here and just focus on the 3D coordinates, also known as the point cloud geometry. Point clouds have many emerging applications. It's also a challenge to store and transmit this data because they are highly irregular, unlike images that are defined on regular 2D grids. And there's also a lot of sparsity in them. And first, we'll look at an approach that is mostly a lossless compression procedure based on octrees. An octree is an efficient data structure for representing sparse point clouds. And the game plan here is that we'll first convert a point cloud into an octree, and second, we'll losslessly compress the octree. In the first step, we'll build an octree by recursively dividing the space into 8 partitions and keeping track of which of these partitions or octants are empty versus occupied. By occupied, I mean that they contain any point from the point cloud. And we'll only recurse into the occupied partitions. And we repeat this enough times until a desired resolution is reached. And this results in a tree data structure where each node in the tree is associated with an 8-bit bit string indicating which of its children are occupied or not. And step 2 is now conceptually straightforward. We will serialize the tree, for example, in the breadth-first search order, and then entropy code it. And for entropy coding, we can use an autoregressive entropy model and use neural networks to extract features from previously encoded nodes to form our entropy model for compressing the current mode. Alternatively, we can also do lossy compression with a compressive autoencoder like we already do in image compression. Again, we'll do this in 2 steps. In the first step is called voxelization. And here what we do is that we will tile the space with tiny little volume cells or voxels and mark each cell 1 if it contains any point from the point cloud or 0 otherwise. And this essentially converts a point cloud into a binary valued signal over a 3D grid. Now, we already know how to compress images, which are basically signals defined on 2D grids. So in the second step, we can just apply nonlinear transform coding to this signal, but we'll use 3D convolution instead of 2D convolution. A naive implementation of this is going to be wasteful, especially on sparse point clouds, where we'll be running this 3D convolution on lots of empty voxels. So in practice, these methods often will partition the space into larger blocks and use an auxiliary data structure to keep track of which blocks are actually occupied versus empty, similar to this octree idea. Now I'll hand it over to Karen, who will introduce relative entropy coding, which essentially re-examines how we transmit information in lossy compression.
Let us reflect for a moment on all lossy codecs that we have been talking about so far. Recall that we built them by first encoding images with a deterministic mapping to a discrete latent representation Z. Subsequently, would use an entropy coder to encode the latent representations losslessly. We restricted ourselves to deterministic encoders, naturally, because entropy coders rely on deterministic mappings. Recent research has been asking 2 questions, though. If we had a codec that could make use of stochastic encoders, would that have any benefits? And of course, what would such a codec look like? So let's summarize. Why could we benefit from stochastic encoders? An obvious argument would be that the class of deterministic encoders is a subset of stochastic encoders, and thus we would hope that we can solve any rate distortion problem at least as well if we consider them. However, from a practical experience, we know that additional noise in any SGD-based optimization scheme might mess up our solutions. So here we cannot really declare this point as a benefit. The main argument that I see for having stochastic codecs, though, is that it would allow for the transmission of continuous signals, and since most generative models are continuous latent variable models, we could use generative models out of the shelf without any modifications and potential performance degradations to them. But how about, are there any theoretical guarantees? Can we say anything about that? Well, we know that there is always a deterministic encoder that is a solution to minimizing the Lagrangian of a rate distortion problem. So this is somewhat a discouraging result, meaning stochastic encoders wouldn't have any place here in theory. But of course, when we change the setup a little bit, namely that we add a conditional constraint, namely when we expect the reconstruction to be reasonably from the data distribution, or in other words, then we expect the reconstruction to be a realistic image. In that case, stochastic encoders provide a provable benefit in theory. So let us go and try to build codecs for stochastic encoders. First, though, we want to set a formal goal on the type of codec we want to achieve. For this, we will borrow a recent definition of relative entropy codecs. So we require a data distribution and a publicly available proposal distribution and source of randomness. And when we say publicly available, what we mean is that sender and receiver both have access to them. So for example, an operating system, that would be the same pseudonumber random generator. So our goal is to represent a sample from the target distribution with our stochastic encoder Q with a binary string whose length is proportional to the mutual information. So that's the goal, but why is this definition and why this bound that we're trying to achieve? So recall the rate distortion function that Yibo introduced earlier. Note that the optimal rate is characterized by the mutual information, and then we can rewrite the mutual information term here in terms of an expected KL divergence. Here we can see the similarity to lossless coding. Relative entropy codecs are optimal solutions to the reverse channel coding problem per sample, similar to entropy coders that solve the source coding problem. Now, let us go ahead and go through some proposals to build such codecs. So you might have noticed that the optimal code length of a relative entropy code appears in the Nelbo bound. Hence, we might be able to reverse engineer a codec. So starting with the loss-leg codec that implements the Nelbo bound, the bits-back codec, how would we have to change the bits-back codec for lossy compression? So recall the encoding procedure. We first remove bits from the bit stream to sample from Q, and we now encode X and subsequently the sample from QZ. Now, if we just leave out the step that encodes the residual between our prediction of X and X, the expected code length is exactly our bound. So here we leave it out. But here's the problem. Let us check out the decoder of this proposal. First, we would recover our sample from Q. In order to now recover Q itself, we need X, but we do not have access to X because we never actually did encode it. Hence, bits-back coding is not applicable to lossy compression because it does not provide a uniquely decodable code. So let's try something else. And let's start with a method that will give us a valid codec, and we worry about the correct code length later. So we can develop a codec based on rejection sampling. Recall rejection sampling? First, we need samples from a public proposal distribution and a public source of randomness in the form of uniform samples. Now our goal is to generate a valid sample of Q, and we can do that by taking our uniform random sample and comparing it against the normalized density ratio of Q over P. So to understand what I mean when I say normalized, consider the unnormalized ratio. Now our goal is to press all values into the range between 0 and 1, and this is easily achieved by computing the reverse ratio and looking for the smallest value. And this value will be our normalization constant. We will call that W. We will accept a sample from the proposal distribution P with index n to be a sample from the target distribution Q when our uniform sample is smaller than the normalized density ratio of the proposal sample. So back to the codec. So how can we turn now this rejection sampling process into a codec? So the idea is to store not the sample, but the index n of an accepted sample with an entropy coder. So if we want to use an entropy coder, we need to know the marginal p of n. So what is that? So note that we can consider the event, if a sample is being accepted or not, to be a Bernoulli random variable. By computing the expectation of acceptance, we can compute the coin toss likelihood, and that comes to be our normalization constant. And hence the likelihood for our sample is a geometric distribution. When used in an entropy coder, the code length of the binary representation is going to be the entropy of the geometric distribution. And to be more clear, we can bound this like this. So what have we done here? So our proposal of coding indices instead of samples themselves helped us build a valid codec. It's fantastic, but there is actually no rate guarantee. So it is not an optimal codec. So this is not a relative entropy codec. And even worse, the runtime of accepting a single particle might also be as bad as the exp of the Rayleigh divergence of Q and P. So first, we want to fix both of these things, but first we want to do better in terms of rate in the next proposal. But what we in the next proposal are going to stay with is the general idea of coding indices instead of samples. So the solution to our problems is another sampling scheme and a respective codec. For this one, again, we need samples from our public proposal distribution and a public and ordered samples of a homogeneous Poisson process on the real line. We will accept a particle only if it is the solution to minimizing the product of the density ratio and the ordered arrival times. Hence, the acceptance becomes more likely as time goes on. For this particular sampling scheme, we want to use the same trick again, namely store the special particle index with an entropy coder. So Lee and Algemal show that the marginal distribution for this random variable is its Zipf distribution, with parameter depends on the KL divergence. So there's nothing we can show here, it's quite complex, but essentially we're going through the same steps as in the previous proposal. So when computing a bound on the entropy of this distribution, we will find the KL divergence will reappear. And this is new. So this is in contrast to the previous proposal. And since this term's largest contributor is the KL divergence, we in fact have identified a codec that is optimal. So we found our first relative entropy codec. It's fantastic. A side note with respect to the runtime though. In its naive form, the runtime is quite bad. However, active research has been going into improving it under minimal constraints. Specifically by making use of A-star coding, the runtime of this algorithm can actually be reduced significantly. Not enough though to be practically useful for applications such as diffusion models. Hence, we're looking for relative entropy codecs with less than exponential runtime. The bad news is though that it can be shown that the worst case complexity is exponential in the KL without assumptions on P and Q. So we need to make drastic constraints on the complexity. So in this case, we will restrict ourselves to uniform distributions for the proposal and the public randomness. We propose the following codec. Encode the integer n that comes out if we round a proposal sample and transformation of x with an entropy coder, and decode by adding uniform noise to the integer n. And it turns out that Zn can be considered a sample of the following distribution. So we basically are using the equivalence of these operations. Here the coding cost was shown to be the conditional entropy. So on average, drawing each Z will cause the KL divergence of Q and P. So what we have done here is we achieved a relative entropy codec. However, since our codec induced a very specific distribution of Q, we're actually quite restricted in the kind of distributions we can represent. So there's ample space for finding new solutions in this area.